wave, which is surface wave, is sensitive to the viscoelasticity change on nearby the surface of the delay line. So this graph shows the one example. I changed the bulk viscosity, so the bulk solution viscosity on the top of delay line, and observe the phase shift, which is the output of the sensor saw device. And you can see the change depending on the bulk viscosity, and shows a clear linear relationship. And I also use the aura protein as a surface modification. And this aura 85 protein, especially, it has a structure of protein G fused to aura protein scaffold. And this has, we took three advantages of this protein. So one is a protein G. As you may know, that the protein G allows us a good orientation of antibodies on the sensor surface, which means we can obtain the high capture antibody densities on the sensor surface. And this aura protein scaffold shows the high pH resistance, which allows us to regenerate the sensor surface by changing the pH multiple times. And the third is the cross-linking between the capture antibody and the protein G. By doing this, we could skip the one procedure in the sandwich assay, because the capture antibody will remain on the sensor surface. So in the end, it shortens the measurement time. So these are the picture of the setup and the surface acoustic wave device. And the device was developed, fabricated by depositing 90 nanometer thick gold film on the top of quartz piezo element. And this part shows the procedure of preparation and with the sensor and the repetitive measurement of the F1. First of all, the gold film, on the top of gold film of the delay line, it was modified with the aura protein, self-assembled monolayer of the aura protein and the polyethylene glycol thiol. And then we immobilized the capture antibodies on the top of protein G to prepare this saw immunosensor. And then we conducted sandwich assay by adding the F1 and the detection antibody, and obtained the results. And in the end of the experiment, we regenerated the sensor surface, meaning removing these del F1 and the detection antibody from the sensor surface by changing pH. And by repeating this procedure, we conducted a repetitive measurement or semi-continuous measurement of the F1. So first of all, we optimized the capture antibody binding condition to protein G. So this graph shows the sensor responses to capture antibody bindings. So at here, we added capture antibody, and the phase is changed over the time. And it was observed that this phase shift is dependent on the buffer solution pH. So these results are summarized here. The amount of capture antibodies bound on protein G peaks at when using a pH 6 buffer solution, which is 4 times larger than when using pH 4. And we also investigated capture antibody concentration dependency on the amount of bound antibodies. And when using the capture antibodies over 100 microgram per milliliter, the amount is saturated. So we decided to use pH 6 and 100 microgram per milliliter capture antibody solution in the following experiment. And then we cross-linked the capture antibodies to the protein G by using PEG5. And advantages of cross-linkings are the capture antibodies can remain through the regeneration, and also it reduces the dissociation, naturally occurred dissociation of capture antibodies from the protein G. So this graph shows the responses while cross-linking. When after adding the capture antibody, the phases shift, and we waited for 10 minutes, and we added cross-linker and waited for another 10 minutes.